mean, sometimes like attendance is part of the grade,
Yeah.
and if you don't have like
I have a
an excused absence.
That's what I'm gonna say.
Okay, we have, what have we done? Additions and dissociations. Two more. We have displacements, also known, I believe our book calls these replacements. Yeah, that's not as good. Displacement's better. And in fact, the word that gets used at the higher level is that these are substitutions. And in a displacement reaction or a substitution reaction, you have something like this. That there is already a chemical bond between these two atoms or ions. And something else comes along that makes a better bond to one of them and just kicks the other one off. If I took copper bromide and I added chlorine to that, chlorine gas comes to us delivered by nature as two chlorines stuck together. That's going to be a theme. Lots of our gases are two atoms stuck together. Hydrogen is H2, chlorine is Cl2, oxygen is O2, nitrogen is N2. Lots of the gases are two atoms stuck together. That chlorine makes a better bond to the copper than the bromine does, so it just pushes it off the molecule, off the compound.
And that's because they are in group.
Now, chlorine and bromine are both in the same group. They're both in group 7. 7 has a trivial name. They're called halogens. Those are both in the same group. So they have the same type of reactivity. One's better than the other. There's a thing called the electrochemical series that I think our book hints at this point, but then we do in a little bit more detail in chemistry too, of if I just throw all of these things together, which ones are more likely to react? Because all the atoms, if they're in the same group, they'll have the same trend, but something's got to be more reactive than something else. Okay.
So how do we know that they have two atoms?
There's not a simple way to, there is a simple way to figure it out. The simple way to figure it out is chapter 6 and 7. Yeah. Can you wait?
As long as I don't need to know it for the test.
You don't need to know it for this test. Things, the chlorines, the oxygens as a gas, they're not ionic, they're covalent. And because they're in group 7, 7 plus 1 is 8, that's our magic number, it means they always make one bond. So when chlorine bonds to itself, it does it one time. Here's why I prefer displacement than over replacement, because saying double displacement sounds better than saying double replacement. So there's alliteration in it. And what a double displacement is this, but everything is in play. Absolutely everything is in play. So what we're going to see is I have a compound where A is attached to B. And I have another compound where C is attached to D. Now, I've been paying attention just a little bit. And I know that in any compound that's written down, in this compound, AB, what does A represent? A metal, which means C is a metal as well. And it means that B is a non-metal and D is a non-metal. So what we're going to do is we're just going to switch the pairing. But I'm not going to pair two metals together because that's not how we make compounds. I'm going to make two new compounds. So A is going to let go of its non-metal and pick up the other non-metal. And C is going to let go of its non-metal and pick up the other one. So AB becomes AD and CD becomes CB. At first, this seems like, oh, that's quite a lot to keep track of. Yeah. It turns out that this type of reaction is the basis of all acid-base chemistry. Remember, hydrogen is in group 1. So it makes compounds the same way that everything else in group 1 does. It can be out front as a unipositive cation, just one plus here. And this is a base, sodium hydroxide and hydrochloric acid. And when they come together, I think I said this out loud a couple of days ago, when acids and bases react together, they always make what? They always make water. Let's try and keep track of that. Let's take the front part of this compound and the tail part of that compound and stick them together. This is an acid, this is a base, and I just made water. Every acid, when it interacts with base, undergoes this reaction. This is called an acid-base neutralization reaction, and it is a double displacement. That leaves me just to take care of whatever CB is over there. What is CB? Very, very quiet, but I did hear it. It's like a theater whisper. Acid plus base makes water plus salt. And in this case, I have hydrochloric acid and sodium hydroxide. Making water and sodium chloride. And it's true for all of them. Name me another acid. Come on, it hasn't been that long. We did him on the board a couple of days ago. We named 4 or 5 acids.
Nitric acid.
Nitric. So if I switched out this chlorine for an NO3, this would read HNO3 plus NaOH makes H2O and NaNO3. Acid plus base still makes water, but now my salt is sodium nitrate instead of being sodium chloride. And if instead of using nitric acid, I used sulfuric acid, what if I changed my base to potassium hydroxide? I would still make water. That's the important thing. Water is the incredibly stable molecule. This is the important thing here. But I would make potassium sulfate. Okay.
Questions about that? Yeah.
So I remember you said something like whenever they bond, they always make like a salt. Like, so how do you make a salt?
This is dissolved in water. This is dissolved in water. This itself is a liquid. And then this gets to be dissolved in water. So the salt that you've made is still in solution. But if I've got an equal number of this and that, then I've just made salt water. I've taken something that was acidic and something that was basic. And, you know, acids, when they splash you, can be dangerous, and bases, when they get in your eyes, can be really dangerous. And if I neutralize them, I just made salt water. If I want to get that salt out, I let the water evaporate. Oh, and I made salt. If I did HNO3 and KOH, I would still make H2O, but I would make KNO3. And my salt, in this case, potassium nitrate. Okay. You switch the front of the acid with the tail of the base. That's the important part. That makes the water. Everything else just floats around in solution.
Is every molecular bond?
These are ionic bonds. These are ionic bonds. This one here, that gets to be a liquid, that one's different. That's a covalent bond. This is a molecule. Everything else is an ionic compound. The ionic compounds go positive and negative and then stick together by attraction. These ones do something different. Chapter 6, chapter 7. Okay.
I wonder if now's the right time to say it.
Let's do it. Because I'm getting questions about ions and salts. Let's take a second to know this. I have a beaker. And inside that beaker is pure water. And inside this beaker is salt dissolved in water. I have two beakers. You get a prize if you can tell me which one of those beakers contains the salt. How'd you do it? You could taste it. What if the salt was sodium cyanide? Which is why we don't taste the chemicals anymore. Yeah, so you could taste it if you were guaranteed it was only sodium chloride, because you did it yourself, you were in control of it. But if it was somebody else did it, you wouldn't be tasting somebody else's chemicals. You can evaporate them to dryness, and one should be dry and the other one would contain salt at the bottom. Okay. The sample that I'm asking you, and now I say, well, the sample I'm asking you to test is not the size of this beaker. I've got a tanker truck, 2 tanker trucks outside. One of them's got water in it and the other one's got salt water in it.
You're going to evaporate them both to dryness? No.
Did you put something in it that only reacts with the salt?
Okay. But then you would have to do it to both, and now your pure water isn't pure anymore. It's a good idea, though.
Couldn't you just take like a small amount of that water and test it? You're not polluting.
If I took
A battery. This is actually a cell. Batteries are multiple cells all stacked together.
and I attach that to an electrode, and I also attached it to a light bulb, and then I put another electrode
Inside the water. What happens to the light bulb? Nothing happens to the light bulb.
because pure water is an insulator. However, when I do the same thing with the salt water, the light bulb comes on.
Because ions in solution split apart. They act as electrolytes.
And they conduct electricity.
I'm going to check just a second. I'm going to check the upcoming test. Just to make sure that there is or is not a question about electrolytes on the test. If there is, I'm going to tell you some more.
If there isn't, I'm going to tell you it later.
Okay.
We're going to come back and look at acids and bases again later on. We're going to talk about pH. And when we do, we're going to stress the fact that because this splits apart into two ions in solution, and this splits apart into two ions in solution, and that one doesn't, and this splits apart into two ions in solution, that the only thing that matters is that H plus, and the only thing that matters is this OH minus, and everything else, the chlorides, the sodiums,
They don't matter.
they don't matter.
Okay?
Later. Let's balance some reactions. Okay, I'm going to do a couple of things. I'm going to give you a question that you cannot possibly answer. And then we're going to work through all of the steps. And there's 6 steps to being able to answer this question. And we're going to discover what it is that you need to know as you go. And then we're going to do it again. Okay, so this first one is a little voyage of discovery. And then once you know how to navigate, the second one will be quick. So the two reactions that I'm most likely to stress are the combinations, also called additions or synthesis, and the double displacements. The double displacements are really, really important because they are the basis of all acid-base chemistry. We're going to do lots of those. And the other one is an addition because combustions are additions, they're combinations. So the two things that you're most likely to get are a combustion and or double displacement. Okay. Question? Nope. Can I give you an amount? Let's think. One of our stated learning objectives for this course is you can take a verbal or written order and convert it into chemical notation. 36 grams of carbon burns in atmospheric oxygen to make carbon dioxide as the only product. What mass of carbon dioxide is generated? Okay. 6 steps for figuring this out. Some of these steps are really, really small. Step 1 is you need to write a balanced reaction equation. Okay. In a reaction equation, reactants are on the left, products are on the right. Do it yourself first before I write it on the board. It says in the question what the reactants are. It says in the question what the products are. A balanced reaction equation does not need names, just needs the symbols. I'm writing them out so that you can see where stuff goes. It says in the question, carbon and oxygen are reactants. There's only one product, it's carbon dioxide. There's three names in this question. 2 of them are reactants. 1 of them is a product. Carbon is just C. Oxygen, well, that's its symbol on the periodic table. I already said this morning.
As a reminder that it's O2, and I had said it earlier in the week.
Oxygen gets provided to us by nature as diatomic molecules. If you write this down as O, you're doing it wrong, because there's no O atoms floating around in the atmosphere. There are O2 molecules, but no O2 atoms. And then carbon dioxide. Okay. Here's how we balance a reaction. We do an atom count. On the left, there is 1 carbon and 2 oxygens. Here's the 1 carbon, and then look, 2 oxygens. And on the right, there is 1 carbon and 2 oxygens.
Oh, that one was easy. It's our first time doing it. It's going to be easy.
Okay. I have written a balanced equation that describes this. We could make it a little bit better. We could tell the reader that this was a solid. The carbon was that gray powder, the graphite that's in your pencil. We burnt it. And we burnt it in atmospheric oxygen, it says in the question, which means it's a gas. Oh. The question didn't tell us carbon dioxide was a gas. On a test it would. Those state symbols add a little bit of clarity, a little bit extra. They're not always essential. Okay. Step 2 is deciding what to do about the numbers. Okay. This is 1 and 1 and 1. And when the numbers are 1, we don't write them in. We only write them in when they're any number other than 1. Okay, so if I start with one of these and I end with one of those, and I look in the question and it says you got 36 grams of that. Doesn't that mean that I get 36 grams of this? Isn't my answer just 36 grams? You're shaking your head, no, this is going to make me very, very sad. Why not? You mean I have to do more work? Yeah. This cannot possibly be 36 grams. Why not?
Yeah.
Okay.
Doesn't necessarily mean.
I start with 36 grams of this. Why do I not get 36 grams of that?
Because part of it's being burnt.
Because there's an infinite amount of oxygen.
There is an infinite, almost infinite amount of oxygen. Okay, let's think. This is a CO2. Let's have
The carbon's a boy and the oxygens are girls, right? I'm going to need a volunteer. He's not looking up. All right. Oh, in times of COVID, we're not allowed to hold hands. So we're just going to have to pretend to hold hands.
You are the carbon. You stand on the scale, imaginary scale. There you go, good boy, you stood on an imaginary scale. And you look down and you weigh 36 grams. I'm going to need an oxygen and an oxygen to join and pretend to hold hands. Pretend to hold hands. You're not actually allowed to hold hands because COVID. And now when you look down at the imaginary scale, does it still read 36 grams? No. No, it doesn't, thank you. That's all we needed. No. The end product contains all the carbon that I put in, plus something else. It has to be heavier than 36 grams. But how much heavier than 36 grams? Oh, I know. I'll look up and see in the question how many grams of oxygen I added. I added all the available oxygen that was in the atmosphere. Gonna have to figure it out. These numbers that go in front of the reactants and products in the equation, they are not gram amounts. They are not gram amounts. The stoichiometry represents mole amounts, okay? So my steps 2 and 3 and 4 and 5 are all about using stoichiometry to figure out how much I make. And then step 6 is actually figuring out how much I make. Okay. So before I even get to 2, I'm going to tell you why there is a second step. The stoichiometry here, which is 1 to 1 to 1, one reactant and one reactant makes one product, does not represent gram amounts. It represents mole amounts. Okay, so we have to define what this new thing is. What is a mole? A mole is a, I'm trying to figure the word, begins with an R, not representative, relative, there you go. Mole is a relative mass. Okay. When we look at the periodic table and it tells us that the mass of a hydrogen atom is 1 atomic mass unit, and that the mass of a carbon is 12 atomic mass units, and that the mass of a chlorine is 35.5 atomic mass units, that's something we have to take into account. So this relative mass that we're going to use takes into account that different atoms have different mass. For us, it's going to be a number that is easy to calculate. It is the gram amount in the question divided by the mass number on the periodic table. Okay? This might be the single most important thing that I say all term. At least the most useful. It's going to be the thing that we come back to the most often. That we cannot use mass directly in a lot of our calculations. We have to convert it into something relative, and the relative amount is called a mole. Okay?
So here's step two. Step two is find the atomic masses of all of the reactants and products. Okay. I have carbon plus oxygen making carbon dioxide. I look on the periodic table and I find that carbon has an atomic mass of 12. 0.01 gram. And then oxygen has an atomic mass of 15.994. But I'm not using a single oxygen atom. I'm using two of them stuck together. And then for the carbon dioxide, I have 12.011 and 2 times 15.994. This, where you add the atomic numbers together, is called a formula mass. And the formula mass is the sum of the atomic masses. Okay? Look at what's in the chemical formula and just add the atomic masses together. So this is a 12, this is a 32, and that's a 44. If you want to tell me what the decimal places are, I will gladly take them. Let's just do 2 decimal places on each. So 12.01, and then what, 31 point what? Nine eight. And 44, what is this one? Close to 44. 43.99. Okay, those are our masses, atomic masses. Let's turn those into moles. I'm going to list the moles of the reactants and products. Have carbon and an oxygen making carbon dioxide. You don't have to write this out every single time. I'm doing it the long way so that we don't ever have a doubt. Where did that number come from? Okay, what is the mass of carbon in the question? So moles, right? Moles is mass divided by atomic mass. For this step, we actually don't need, we only need to do the reactants. So moles is mass divided by atomic mass, which for carbon is 36 grams divided by 12.01. Okay, let's take a second. what are my units for atomic mass?
AMU.
They're atomic mass units. Today is going to be the last day that we ever call them that. Because we're going to switch atomic mass units to being something a bit more useful. If moles equals mass divided by formula mass or atomic mass, and moles are in moles and mass is in grams, then what's the unit here for formula mass or atomic mass? What is it that I divide grams by in order to equal moles? The grams have disappeared. If I divide grams by grams, then the grams cancel and I just get a number. Yeah? If I divide the gram that's in the denominator by something else, when you divide a number by a number that's then divided by another number, what happens to the number at the very, very bottom? It goes all the way to the top. You can do this yourself. Look at this. Take 1 and divide it by 1/2. What's the answer? 2. Because that 1 and that 1 cancel and the 2 rises to the top. So what do I have to put here to make grams divided by something equal moles? The periodic table has done it again. It's just turned into a giant cheat sheet. It now tells you how many grams are in a mole, a relative amount of every individual atom. We're going to now only talk about atomic masses being written as grams per mole. Okay? All right, 36 divided by 12. Very, very low on the board. Hopefully you can see it. 3 moles. I have 3 moles of carbon. How many moles of oxygen do I have? I have the entire sky's worth of oxygen to do this reaction with. So I have an infinite number of moles of oxygen. All right. I said some of these, it's 6 steps, but some of these steps are going to be very, very, very short. 4. 4 is we're going to identify the limiting reagent. Limiting reagent is the reactant in the smallest mole amount. Okay? And my reaction is carbon plus oxygen makes carbon dioxide. And I've discovered that I have 3 moles of carbon and an infinite number of moles of oxygen. Here's a question. Which is smaller, 3 or infinity?
3.
3 is smaller than infinity. Therefore, this is the limiting reagent. This means that however much carbon dioxide I make must be based on that value. I cannot make more carbon dioxide than the amount of carbon that I put in, because this limits my math. Okay, I have an infinite number of oxygen, but a limited number of carbon. Okay.
5. Use the reaction stoichiometry to predict moles of product. Okay, again, I have carbon plus oxygen making carbon dioxide.
And the stoichiometry on my balanced equation
Said if I had one of these and one of those, I would make one of those.
It turns out that I don't have one oxygen. I have an infinite number of oxygens. And that I don't have one carbon. I have 3 moles of carbon. The stoichiometry in a reaction like this is the number of moles. I've got 3 carbons. What's 3 moles of carbon? What's the maximum number of carbon dioxides I can make?
3 moles of carbon dioxide.
Let's see how much time I have. Oh, I've got 4 minutes. I can slow down. Six.
Convert moles of product to mass of product.
Moles equals mass divided by formula mass. FM, formula mass. If moles equals mass divided by formula mass, and I don't need to know moles, because I already know moles, what I need to know is mass. If moles is mass divided by formula mass, what does mass equal? Moles times formula mass. If I take something across the equal sign, and that something was a denominator, it's on the bottom of this division. When it crosses the equal sign, it becomes a numerator. Moles times formula mass. Mass is moles times formula mass. Number of moles is 3. Formula mass, 43.99. Look, I'm putting my units in here. The moles and the per mole cancel. Gives me an answer that is in grams. Four times 3 is, shouldn't need a calculator. Use a calculator if you got, if you 132. Okay. We have defined a process. Step by step by step by step. There is only one equation. That's it. Moles is mass divided by formula mass. We used it forwards and backwards to turn mass into moles, our relative unit, and then back again. Do another one on Friday. Okay?